We have here Thinh, Nguyen, Dmitry Yatsenko, and Shan Chen from DataJoint, and take it away.
All right, thanks. Let me share my screen. All right, hi everyone. My name is Thinh Nguyen from DataJoint, and thanks for joining me here in this breakout sessions on DataJoint and NWB interoperability. In today's sessions, I will first go through a brief introductions about DataJoint, and the main focus of today are to go through the different modes or different options of for interoperability between DataJoint and NWB that we've worked together for the past year or so to put together some different approaches to integrate DataJoint and NWB. And then I will go through some demo, and of course we will have some form of discussion on how useful that would be, or any feedback would be great. All right, so let's get started. All right, so as you know, the data for neuroscience, data are getting bigger, richer, and more complex. A typical study now are typically multimodal, where we would have to deal with a huge amount of data, from behavior data to imaging, electrophysiology, optogenetic stimulations, and especially with multi-lab collaboration, the amount of data is just growing larger and larger. Hence the need for standardization such as NWB, but also a more useful tools for managing data. So in terms of tool for managing large amount of data, traditionally we have a relational database system, and so typical relational data model offer a good solution for complex data and metadata, and that would ensure data integrity, support flexible queries. But however, relational database such as MySQL, SQL Server, those are not very efficient or useful for sophisticated computations, and obviously they're not very friendly for neuroscientists. Right? The SQL syntax is not exactly the easiest thing to work with, and on the other hand, we have high-level programming languages that we are all very familiar with. These are MATLAB or Python. These are good for sophisticated computations. These are friendly to neuroscientists, and we use them through most of our training, our work. But however, these tools, these languages are not very convenient or useful for storing or working with complex data storage. So building on top of these frameworks, DataJoint is a workflow management system that would allow you to work using MATLAB or Python, interact with a relational database system that would provide a way for you to build your data pipeline, ensuring storing data and metadata, and capturing their dependencies, constructing as like a workflow, a pipeline. And DataJoint has built-in distributed computations that store the code for your analysis at each level of your tables or entity, if you will, and that would take care of distributing the computation for you. So if you want to populate or execute any computation at any level, the parallel distribution is built in. So with that, I want to quickly go through a demo on DataJoint. Hopefully everyone's are somewhat familiar with DataJoint already, but let's just go through that one quick demo just to recap, okay? So I have this Jupyter notebook here open. Can you see my screen? I'm assuming yes. If you don't see it, let me know.
Yes, we can see it.
Oh, perfect. All right, so as I mentioned, DataJoint, here I'm showing a demonstration in Python. DataJoint is a framework that allows manipulating or working with MySQL databases, tables in Python. So a quick recap here. So first, I would just import DataJoint as DJ, and then I would start by creating a schema. A schema here serves as think of it as like a folder to contain all of your tables. And also here, DataJoint schema equals to DataJoint schema here. This also create a way of connecting to the database. So, right, so I am now connecting to my local database here. And the first thing I want to show is to create a table in DataJoint. So creating a table in DataJoint is similar to creating a new class. So here I want to create for example, creating a table mouse. I can put the schema, my schema as a decorator here that would basically create a corresponding mouse table in my database. And this table, I have 3 attributes here. The definition of my table here, I have 3 attributes: mouse ID, date of birth, and sex. So mouse ID is of type integer, date of birth is date type, and sex is an enum of male, M, F, unknown. So DataJoint support all of the MySQL data type. So int, varchar, long blob, for example, float. Here, I also want to mention this special notation here, this dash dash dash. This represents a separator between the primary attributes on top and non-primary attributes following that. So here, by defining my table this way, I'm basically saying that mouse ID is my primary attribute that would make up of my primary key. So one mouse is uniquely identified by one mouse ID. And these data birth and sex are non-primary attributes. So let's do that. And here I am just displaying the mouse table. So right now, as you can see, I don't have any data here, but at least you can see the table that has 3 columns here, right? Mouse ID being bold type, representing this column is part of the primary key, right? Just as we defined. And then date of birth and sex. So next, I want to show how we can insert data into DataJoint table. So inserting data into DataJoint is as simple as specifying a list of tuples corresponding to your attributes. So right here, I want to insert 3 rows in a way, right? 3 rows, and I can do that by specifying 3 tuples here. The first element corresponds to the mouse ID, and then date of birth, and then sex. Okay, let's do that. And then the insertion is done by just doing the table dot insert and put your data in. All right, let's see what's there. Okay, so now we're just inserting 3 entries here. As you can see, we have 3 now. Now, let's insert some more. You can also insert data into DataJoint table in the form of a list of dictionaries. So you can as you can see here, the first way is to do it by a list of tuples, or you can do it by a list of dictionary. So here, with a list of the dictionary, you have to specify the key being the same as the table attribute. So mouse ID, date of birth, and sex. Okay, and then same way, right? Call the insert function. Okay, let's look at the mouse table. There we go. Now we have 4 entries here. Okay, next, let's create another table. I will create next the session table. Again, the schema decorator, and then a class called session with a definition for the table. In this definition here, I have this special notations with an arrow point to the mouse. This is basically saying that I want one of my attributes to be a foreign key reference back to the mouse table. And because this mouse is above this primary attribute separator, basically I'm saying that I want my mouse to be part of my primary key. And another attribute, also a primary attribute, is a session date. So in this way, my session table has 2 things as that's make up of its primary key, the mouse and the session date. And then experimenter and setups are non-primary attributes. Okay, let's run this and show the session table. So, okay, as you can see here, the session table doesn't have data, but you can see the column's name right here, right? So the column's name has a session date, bold type, meaning primary attribute, clear, obviously. But it also has the mouse ID, which is the primary attribute for the mouse table. So in this way, we can chain the dependency. This is one way for DataJoint to represent dependencies, and we can always refer back to table parents table. Okay, so let's insert some data here. Okay, so I am here showing insertion of data in the form of a list of dictionaries, just like before. I have to specify all of the attributes for this table. So mouse ID, session date, experimenter, and setup. That, and then dot insert. Okay, let's look at the session. So now we have 4 sessions inserted, 2 from mouse 0, and 1 from mouse 1, and 1 from mouse 2. Okay. Next, DataJoints allow you to do very flexible and powerful queries. So one example is that I want to look at all the mice with the sex equals to male, right? So male, right? I can use this special syntax here, the restrictor syntax. So basically, this reads as mouse restricted by sex equals to m, and then I can, at that point, I get back a look into the table, into the mouse table that has this restriction. So clearly here, I can see all mouse 3 passing that restriction. The next type of restriction is restricting by a session, so by another table, really. So here, I want to get the mouse that is restricted by containing session. So restricted by session, meaning I want to get all the mice that has session. Okay. There. So now I get mouse 0, 1, and 2. These 3 mice have session with them. Or I can do the other way around. I can say, okay, I want to get all the mice that has no session. So I can use this subtraction here, basically an anti-restriction. There. So now I can get mouse 3 and 4 having no session. And so these are basically queries, meaning you get a view back to the table, but you don't yet download any data yet. You haven't really gotten any data back to your local workspace. That is done by using the fetch method. So you can do mouse. So here I want to fetch the mouse that has sessions, fetch the data back. So I can do fetch like that. And what I get back is a record array of all of the tuples. So I have like 3 tuples right here, just like how you insert them. I can also fetch back as a dictionary. This is very useful to many people, and I find it's very useful as well. Fetching back with the keyword asdic equals true. This would allow you to fetch back the data in the form of a list of dictionary, and then you can just work with that. DataJoint also allows you to delete records, and deleting DataJoint enforce data integrity by cascading the delete to all of the downstream tables that's referenced by the record that you are deleting. So for example, if you are deleting mouse 2, this is the syntax. You can just do mouse restricted by mouse ID equals to 2 and then dot delete. This basically deletes the mouse 2 and also anything that is downstream of mouse 2, meaning the sessions in our case. All right, so I can do that. And basically, DataJoint would prompt you for a confirmation saying basically, okay, I'm going to delete 1 sessions and 1 mouse. Yes. Right. If you show the mouse table again, we can see that mouse 2 is gone. And if you look at the session, we can also see that all the sessions belonging to mouse 2 are also gone. You can also drop the entire table in DataJoint. So by this dot drop. And again, it would prompt you for, okay, dropping all of the dependencies on this mouse table, which are including the sessions and the mouse. Let's not do that now. All right, so I hope that would give you a quick recap on DataJoint, and so that we can go back to the presentation. All right, so if you want to learn more about DataJoint, if you want to try the DataJoint or going through the tutorial, you can visit this playground here. We recently launched this playground as a Jupyter Hub that hosts for free. You can just log in here. Quickly do that. You can sign in or sign up using your DataJoint account. You just create one for free. And then you can launch your playground environment where we provided a list of tutorials for you to get familiar with DataJoint, starting from connecting to the database, some DataJoint basic, and also specific example tutorial that work with, for example, electrophysiology or calcium imaging type of data, right? Yeah, feel free to try that out. Let's get back to the presentation. So next, let's dive into the focus of today's talk. What are some options for interoperability between NWB and DataJoint? The first way, and perhaps the most obvious way, would be to export NWB files from a DataJoint pipeline. This is simply just to, at the end of your study, you can aggregate all of your data and metadata and write an NWB files object and then just export that out. The second way, perhaps more the next level of integration would be to store that an NWB file object in the DataJoint table column. So in this way, user would be able to insert an NWB file object and then fetch an NWB file object directly, working directly with the DataJoint table instead of having to export into a files and then read the files again. The third level of integrations are storing individual NWB neurodata type in DataJoint column. So such as NWBFile, that's one neurodata type, or device, electrode, electrical series, patch clamp series, those smaller NWB neurodata type can also be stored in the DataJoint column. Okay. Let's quickly, I want to quickly describe the first option, export to NWB files from DataJoint pipeline. At this point, I want to just talk about a quick case study where we have the opportunity to work with Carol Svoboda from Geneva Research Campus, that we take the data from 11 publications. These data are either in .mat format or .nwb 1.0. And then taking these data, we built DataJoint pipelines that are more or less NWB compatible. And then these pipelines would also feature built-in NWB export capability that would export into NWB files. Doing it this way, in a way, we have built or more or less standardized the DataJoint pipeline to be NWB compatible following NWB standard, so that the export routine would any NWB files that are export from this 11 publications are NWB compliant. If you want to learn more on this project, please visit this link. I can share the presentations here with Ryan later. Okay. So as you can kind of imagine, exporting to NWB files from DataJoint pipelines is not so much integrated, right? Really, you just exporting NWB files and then as the kind of like the end product, and then user can just consume those files. It's not so much integrated. There's still quite a decent amount of custom export code to be written per pipeline, right? So if you have a very specialized DataJoint pipeline, you have to write that export code. And you cannot work interactively with the data as part of the pipeline. You only have one NWB files at the end of your study, which you can either archive or publish, but can't really work as part of the pipeline. And this method does not benefit from many of the DataJoint features. There's no data integrity supported. There's no flexible query. You cannot do cross sessions or cross subject queries, right? You still have to like do a for loop and read through all of your NWB files and then just pick the ones that you want. That brings me to the next options for interoperability, storing NWB files objects. So here I want to refer to the NWB file object, and we can store this NWB object in DataJoint table column. Okay. Before we get to the technical implementation of that, I want to do a quick recap on the regular data types in the DataJoint table. So DataJoint supports all of the native MySQL data type internally, meaning the data are saved in the database. These are, for example, integer, enum, varchar, long float, for example. And also DataJoint features kind of DataJoint specific data type that can be stored externally. Externally here means either your local file system or, for example, Amazon S3. And we support 3 types of external data type. But so blob, attach, and file path. But just don't worry about these for now. I want to focus on one, which is file path. So file path is a new DataJoint features that allow for DataJoint to store a file, provided a file path inside a DataJoint table that is managed by DataJoint. Meaning, if you delete from an upstream table that has a downstream that has file path, that file can also be deleted. So query and integrity, data integrity is ensured and managed by DataJoint. So these features allow for DataJoint to work with a collection of files. that can be stored externally. So this is one example of how you can define a table that has an attribute of file path. So here I'm creating a very simple table, NWB sessions that point back to some example upstream session table as my primary key, and NWBFile is of type file path. This way, this NWBFile is actually a file, perhaps stored in my local file system that is managed by DataJoint. Okay, great. So we have a way of storing NWB or files, right? Particularly NWB file, but that still doesn't address the question of how can we store and fetch NWB objects directly, not files, but NWB objects. That can be done via a new DataJoint features that we recently developed in collaboration with Lauren Frank Lab, and that is the attribute adapter features. This is a DataJoint feature that allows for users to define any arbitrary data type in DataJoint. So what does that mean? Okay, let's think of a case. So for example, I have my special data type. This is not Python native dictionary. This is not NumPy array. This is my special class, for example. And I want to be able to save my data type in a table, in a DataJoint table, something like this. So I can define my table this way, which has a data of type my data type. So as you can see, this angle brackets notation here notates the fact that I am using a special type, a special data type. And this can be done using the attribute adapter feature, something like this. The one thing that user would have to define is an adapter class that, for example, my data type, which is an adapter class, a class that's inherited from DataJoint attribute adapter. And user would have to define three things: attribute type, a put method, and a get method. Attribute type is the actual type of data, is the type of native DataJoint type. So for example, this has to be either integer, bar chart, long blob, or file path. And a put method, this put method take in the special data type, your data type, I guess my data type in this case, and define a conversion method that would convert that object into a DataJoint type, the DataJoint type that you define here. This put method is called upon the insert, whenever you call insert. And another get method that you have to define that gets called upon the fetch, that would take the DataJoint type stored in the database, reconstruct back your data object, and return to the user. Okay, so that's basically the adapter class that you have to define to get this to work. Okay, how does that look? How would that look like when you actually use it? So this is an example. Let's say I want to insert into a table my data type, right? What happened is that this would then evoke the put method that would take my data and then convert that into some native DataJoint type, store that in the table. And whenever I call fetch, whenever I fetch back from the table, what happened is that the get method would get evoked, taking the data stored in the table and going through this get method to reconstruct the actual data type and return back the actual your data type. So with these features, of course, we can start thinking about DataJoint and NWB integration by defining a new adapter class for NWB object, right? Exactly. So that take me to the next example here. So here I want to show a very simple kind of a simple pipeline concept. For example, in this pipeline, I have subject and then some sessions associated with the subject. And then from this session, it goes through the rest of the pipeline. This being some EFIS recording, for example, and then spike sorting, wave analysis on the spikes, getting the units, analysis on waveform, whatever that goes through the rest of your pipeline. And then on top of that, I have another NWB session table, another table that meant to capture the NWB file. So the idea is that after I run through the rest of my pipeline, I would have an automatic computation routine that would compute that that would generate an NWBFile object that contain all the data and metadata for the rest of my pipeline for that session. And I want to store that NWB object in a table so I can maybe fetch back at some later time and do further analysis or use any of the NWB tools for data visualization or analysis, right? Okay. This requires an adapter class, just as I described before, right? So I will have to build an adapter class. So something that looks like this. So a class NWBFile, I have to define three things. Attribute type, here I want to define the attribute type to be a file path. This would allow me to actually save that NWB file object as an actual file externally, and can be managed by DataJoint, and the put method and the get method. The idea of this approach here is that for every session, after the entire pipeline has been ran through, you can compute and store a corresponding NWB file in a table for fetch. That would then have one corresponding NWB file per session behind the scenes that you can definitely work with outside of DataJoint. Okay, right. So this brings me to the next demo. So I want to quickly demonstrate how this would work. This is the first one. Okay, here it is. All right, so I'm assuming everyone can see my screen here. This is the next demo that I want to show, how to work with a simple NWB adapter using the attribute adapter features of DataJoint. I import the necessary packages. The objective here is to build that attribute adapter class that would support NWBFile object and use this one in a DataJoint table, doing some insert or fetch. Okay, so first we need to create the adapter class. All right, so this is the code for creating the adapter class that would work with the NWB file. So I'm naming it NWB file adapter. Before that, I have to specify some directory where I want to save all the NWB files. And here I'm getting that from just reading the configuration files that I have already pre-configured. So basically printing here, I want to save all of my NWB files at this root location. Okay. Let's look through this NWB file adapter class. The first thing I need to define is the attribute type. And I'm setting this to be the file path at NWB store type. This NWB store is just a keyword that I have already configured to point to some file location. Like in this case, my local file path, but this can be pointed to, an S3 location. The next thing I need to define is the put method. And what I want to achieve here is to read in an NWB object, save the NWB object at this location, and return a file path like really a file path, like an OS path object. Okay, so let's see what I'm doing here. So first I am extracting build a file name to be saved by just joining the NWB identifier with the .nwb. And taking this name, I am calling the NWB HDF5IO to write method to just write this. And I'm sure everyone's familiar with this step. Just write that there. And really all I'm doing is returning an OS.path object, joining the directory and the file name. That's my put method. My get method is basically reading out this path. Oh, but just a quick note here. This path itself is what gets saved into the table, into DataJoint table. And whenever you call fetch, the get method would get involved. And the get method would take out that path. And this is how I define my get method. Reading that path and returning an NWB object. So calling the NWB HDF5IO read method to return that object. Okay, let's actually use this. Okay, the next thing I need to do is to instantiate this class. instantiate an object this class. Oops, sorry. Okay, and then I can build my table just as before. Okay, connect to local database. I built this simple table named NWB that has an ID and then this NWB, which is a special type in this angle bracket notations, point to the instantiated object here. Okay, all right, so let's just look at this table. So in this case, this table doesn't contain anything yet. The next thing I want to do is I want to insert a record that contains an NWB object, right? That's the whole point. So I need to build that NWBFile object first. So here I am creating some mock NWB object, identifier, giving it some identifier, file creation date, experimenter, also adding a subject here. And as you can see, I have my NWB object here. All right, so adding that to the table. Okay, nothing in the table yet. Calling the insert method, passing in the dictionary of NWB ID attribute and NWB, which is the actual object that we just created. Okay. All right, so there it is. So really what happened here is that the put methods get called, passing in this NWB, write that NWB in my local file directory, and then returning a file path. Here, I can see one record in my NWB table. Now, let's try to fetch that object back, just to confirm that we are able to indeed insert an NWB object into DataJoint table and fetch back the same object. Okay? So you can do that by just NWB restricted by that ID 0, and then fetch the NWB attribute. And let's display that. So there it is. So now we have this NWB object fetched back from DataJoint table that contains the same information as before. And let's see. So as I mentioned before, right, because we are using the file path features, the file path type, all of those NWB objects are actually being saved in my local directory. So I can just display that here. So I'm listing all the data in this NWB directory, and you can see one. So this is, all right, so as you can imagine, if we add more NWB objects, we can get more files here. All right, so this is the end of this demonstration. Let's go back to the presentation. So as you can see, this approach of working with NWB files by storing the NWB file object into DataJoint is, in a sense, more integrated compared to just the export approach. The advantages here is that it's fairly easy to implement and manage. User would only have to build that adapter class, which are fairly straightforward because it's working on the NWB file object level, and really you only have to supply the write the file and read the file. You do have all the metadata and data in that one object and one file. When you fetch back, you have everything. You can use all of the visualization, all of the NWB compliant, NWB aware tools on that object. And this is still queryable and fetchable with all of the DataJoint features. And you can also work with that NWB files outside of DataJoint. However, one of the crucial disadvantages here is that the file itself is generated after the entire pipeline has been executed. So the object is fairly static and it doesn't grow as new data are added. So as you can imagine, if you add more, I don't know, say cell, or if you add more units or you delete units, you either have to delete that NWB object and then regenerate a new object to update, but by itself it doesn't grow with the pipeline. And because you aggregate all the data and metadata into one file, potentially you're dealing with a large physical file, but that's not really, that's as expected, right? Okay. All right, so that brings me to the next approach, perhaps a much more integrated version of NWB and DataJoint interoperability, where we can store NWB Neurodata type in DataJoint column. So basically using the same approaches we used before, right, you can easily imagine that we can build more adapter that not just work on the NWBFile object level, but maybe adapter that works on the individual level of neurodata type. So for example, device, electrical series, patchline series, units, trials, those type of neurodata type, we can build adapter for each and then embedded those attributes along the entire pipeline, the entire DataJoint pipeline. In that way, you can easily fetch or insert, for example, a patch clamp series somewhere and fetch that back and work with that. That's the idea. So on this, I have already prepared, put together a small pipeline on intracellular recording from View Data. And this pipeline, this example pipeline for the sake of demonstration here looks something like this. So this is a diagram, architecture diagram, DataJoint features to show the architecture of your pipeline. So in this one, we start with a subject, multiple subject, and multiple session per subject. And under each session, there can be multiple recorded cells. And for one cell, we have a recorded membrane potential. And for this membrane potential recording, we also need information about the intracellular electrode, the device, and the brain location. So this is a fairly simple pipeline for membrane potential, for example. And what's relevant here is that at each of these four table level, I have used attributes that are NWB neurodata type. So for example, in the session table, there is one attribute that is NWBFile that is of type NWBFile object. At the membrane potential table, there's a NWB patch clamp object of type patch clamp series, which is an NWB neurodata type. And similarly for the intracellular electrode table and the device table. For the demonstration here, I have already built the adapter for each of these four special object type. And my choice of building the adapter is that I decided to let NWBFile to be of type file path, and patch clamp series is also of type file path. So these two would have corresponding .nwb files stored externally. And the device and the IC electrodes here are of type dictionary, Python dictionary. So these are stored inside the database. So this is just my specific implementation, but obviously it can vary. All right, so with this design, at the session level, there is going to be one .nwb files corresponding to this session that contain the information, the metadata from the session and the subject. And then for every new membrane potential, there's going to be a corresponding .nwb files associated with that membrane potential that can reference back the sessions. And the referencing there is done using external link, NWB external link. All right, so at this point, I want to go to the next demo to show how that would look like working with this pipeline. Okay, so let's start. I'm importing all the relevant packages, and I'm showing again here the architecture of this pipeline. And one thing to note, one thing I want to highlight again here is that NWBFile at the session level are stored as a file path externally. The device and IC electrodes are stored as a long blob, meaning like a Python dictionary stored internally inside the database. And NW patch clamp series for the membrane potential, this is also stored as a file path, so it has a corresponding .nwb file stored externally. Okay. Next, so this pipeline, I have already populated all the data. So import all the data and populated all the table here. And here at this point, I just want to demonstrate how it would look like for user to look into this table and fetch some results back. So let's look at the sessions. So in this table, there are 36 sessions, and for every session can be identifiable by the subject ID and the session time, and it has the NWB file here. Sorry. all right? If we fetch back the NWB file here, basically if we fetch back this attribute, I am expecting this to return an NWB object just because of the way I built that adapter, similarly to the previous demo that I showed. All right, so let's do that. So let's start with picking one session of interest. So here I am picking a session that's from this animal and this session time, for example. And using this session as a restriction, I can restrict the session table to that session and fetch back the NWB file. And what I get back is indeed an NWB file object, like an NWB file object that contains all of the meta information that I've already inserted. So for example, the animal, so it has a subject and session start times, all of the meta information there. But as you can see, this NWB object does not contain any of the acquisitions or analysis or processing at all. It's just really the meta information. So nothing about the intracellular data. All right, so let's go next and check the intracellular data. So the intracellular data are contained in this cell table that has some electro information and membrane potential, right? So let's do that here. So next, I want to check the intracellular electro in the cell table restricted by that session of interest. Okay, so I can see here there's one record for that session that the recording is at left hemisphere ALM region from that subject from that session. And it has the IC electro attribute here. This, if I'm fetching this back, I would expect this to be of type NWB Neurodata type IC electro, I believe, yeah, because of the adapter that I built for that. Okay, similarly with the membrane potential. Membrane potential for that session, there's one cell that has the NWB patch clamp. As if I'm fetching this back, I would expect to get back the IC EFIS patch clamp series type. All right, so let's do that. Here I am fetching the electro back. So that can be done by just build that query, right? And then .fetch, and then the attribute that you want to fetch back. If you don't specify anything here, DataJoint will fetch everything back, like all the columns. Okay, so I'm just fetching back that IC electro. Okay, showing that. Okay, so what I get here is indeed a pi NWB IC EFIS intracellular electro object that contain all of the meta information that's relevant here. Okay. Similarly, let's fetch back the membrane potential. So I'm fetching back membrane potential for that session as well. And this is a patch clamp series. Right. So I am now fetching back the membrane potential patch clamp series object. But as you can see, this one is really just that patch clamp series object. It doesn't contain any information about that, the subject of the session, nothing upstream. DataJoint managed that. The corresponding file for this, so actually, yeah, so here I can plot the data as well, just to plot the membrane potential, just to plot. But I also want to show the file structure behind the scene. So can you see my window explorer, or can you only see my Jupyter notebook here?
Just the Jupyter notebook.
Okay, so maybe I share the different screen. Okay, give me 1 second. Let me stop my sharing here and then reshare again. Okay. Can you see this window?
Yes.
Right. So this is where I decided to store my all the NWB file. So in here, you can see that I have a folder called sessions, and here it's contained all of the NWB files corresponding to all of the sessions in this table. Okay. And then I also have the membrane potential that store all of the NWB files corresponding to all of the membrane potential in the table. Each of these NWB files here correspond to membrane potential has a external links that point back to the sessions, to the session files here. Right? So that is one way to basically passing on the management of files and data over to DataJoint. In this way, let's go back to the presentation. Right, so as I just showed there, if we have this entire pipeline, let's just say that we have multiple sessions and we have multiple cells per session and multiple membrane potential per cell, we would end up with multiple .NWB files for each of the sessions and multiple membrane potential .NWB files per sessions, and each of all of these membrane potentials has external link pointing back to the sessions. This design allows for similarly very flexible query and fetch on specific NWB objects. So in this way, you can just, for example, if you're only interested in the electrode, you can fetch the electrodes for restricted by some subject, for example. Or if you want to filter by cell, you can restrict by these 20 cells that pass some criteria, and then you can just fetch back the membrane potential. So this allows for a much more fine-grained and flexible query level. And this design also is dynamic and can be adaptable to new data. So if you have new cells, you would have correspondingly new membrane potential that would be another NWB file stored externally but managed by DataJoint that has an external link pointing back to the corresponding sessions. If you delete some cells, you obviously would delete the membrane potential and the NWB files corresponding to that. So in this way, this whole pipeline, all the NWB files are managed by DataJoint and ensuring all the data integrity. And you can also work with all of these NWB files outside of DataJoint. Given that you have to maintain all the relative path amongst the files, right? Because these files are referenced each other by the external link. So one disadvantages here are the implementation is certainly more complex. You would have to define new adapter class for any of the new NWB neurodata type that you want to introduce here. And different people, different labs may have slightly different implementations. So that would be one, perhaps, disadvantage. It's much less standardized in that way. And I don't know if this is classified as disadvantage, but obviously you would have to work with multiple NWB files and the external links per session. You would have to manage the relative path. You have to be aware that if you move files around or if you rename the folder, that would break the external link. All right. With this, I am almost finished with the presentation. I just want to give a quick summary. DataJoint can be used to manage collection of files with ensuring data integrity and flexible queries. In this way, DataJoint would provide the working on a study managing all of the NWB files, for example, and still enjoy all of the features with all of the NWB tools. And you can also define NWB custom data type now that can be much more closely integrated into DataJoint pipeline, as I just showed. Some future directions, something that's, that we've been thinking about. One of the challenges, or obviously the building those adapters, right, for the neurodata type. And as different labs may have different implementations, maybe one good idea is to have a library of all of these NWB neurodata types that user can just, if they don't want to design that themselves, they can just download and then just use. Or we can move along the line of a full DataJoint pipeline that is more or less NWB aware, that has all of these neurodata type embedded inside and built-in functions to export into NWB files. This brings me back to recently we are very fortunate to receive a U24 grant, canonical data pipelines for neurophysiology. The idea here is that we want to publish a well-curated DataJoint pipeline for neurophysiology that has built-in capability for NWB export and NWB compliance that are basically a turnkey solution ready to go, ready to deploy. So anyone, any new lab or any lab starting with a new project can just take them and just start using them. All right. That brings me next to, well, thanks everyone for your attentions. And I want to have a special thanks to the Neurodata Without Borders team, Ben and Ryan, that helped defining the directions and working with the interoperability. And also I want to say thanks to Carl Sforda and Lauren Frank on developing some of the new features for NWB and DataJoint interoperability. Oh, thank you. I do have some special kind of like specialized slides. If anyone wants to go into the detail of how each of those attribute adapter, the 4 that I built, how are those actually built? I'm not sure if that's appropriate because this is user day, not developer day. So I don't know how much in depth I should go into, but I'm more than happy to go into that if you're interested. Well, with that, thanks, and I will take any questions. Is it in the chat? I think it's in the chat.
Thanks, Thinh. I have to run out and start the next breakout room. I love to see this work, and I'll be if you can send me an email with the notebook,
Yep.
I'd love to play around with it, and then I'll send you some questions that I have afterwards. But
For sure.
You.
Thanks, everyone.
Or yeah, the room will stay in case there's more questions. I just need to run out and start the next room for the next group.
Okay, perfect.